So welcome everyone. This is the second extremal and probabilistic combinatorics webinar. My name is Jan Hladký and we are organizing this together with Diana Pige, Jan Volec and Liana Jepremian. Before we start with the talk itself, let me go through some practical things regarding the webinar and this platform. So the webinar will be regularly on Mondays at 1 p.m. UTC. Please note that because of daylight saving, this may actually be a different hour next week than this week for you. So depending on your location. This week we introduced password so you can't connect. Okay, I mean you did connect to this session, but some of you got an email where you don't have to enter a password. But if you were using the link on the seminar webpage, then you actually need to add a password. So the password is the first 6 prime numbers concatenated. And we will keep this password the same unless there is a problem with this particular one. This session is being recorded. So that means that the speaker will be recorded, and if anyone gets unmuted and speak, then they will be recorded as well. After the talk itself, there will be a recorded part of questions and answers. And after that, there will be another part, which will perhaps be more informal, where we will stop recording. Okay, so if you, for some reason, don't want to be recorded with your question, then you have to wait with that one. We will most likely, we will not, or the way it worked last week is that most questions people had were answered during the seminar by other attendees. So there is a chat, there is an option to chat, and if you ask a question, most likely it will be answered by someone else, by another attendee. If I see that there is a serious question that needs to be answered by the speaker, then I will communicate it to the speaker. But I understand that this is a limitation from people having an opportunity to ask questions sort of in real time as they would normally do. On the other hand, it seems difficult to manage it in such a group and with this such a big group and with this platform. So that's it. And maybe one last thing, on the seminar webpage, we currently linked the slides. So if your question is, what was the definition 3 slides back, then you can answer that question yourself if you go on the seminar webpage. Okay, so now it's my great pleasure to introduce David Gamarnik from MIT. And David will be, so the title of his talk is Overlap Gap Property. And so this is a nice work he has been doing for the last 6 or 7 years, where he connected some combinatorics or random structures with running time or efficiency of a certain algorithm. So it's a really nice talk, a combination of combinatorics and algorithms. So please, David.
Thank you, Jan. Thank you very much for the invitation and opportunity to give this, admittedly, my first webinar, first web-based talk. I hope I won't have to give too many of those, not because I'm not invited, but because all of us won't have to give too many of those talks. I hope it goes smoothly. I'm gonna strictly follow the rules that you just proposed. I don't have that many slides, only 21, which are built to answer questions that you have, but I understand answering questions in real time is might be tricky, so I'll just instead speak maybe slower. Let's begin. So this is a joint work with several authors, and I already immediately see that I have unfortunately misspelled the first name of one of my co-authors. It's spelled with K, but not C. He's from a slightly different community. Probably most of you don't know him, but it's not the reason to misspell his name, nevertheless. While this is going to be structured to give an overview of several pieces of work, and as Jan kindly mentioned, that indeed this is a line of work I've been involved for the past 7 years. Mostly I will focus for the illustration purposes on one of these problems in the field of spin glass models. But let me say right away that you are not anticipated to be experts in statistical mechanics and spin glasses, and I'll try to make the talk as self-contained as possible. And as a starting point, as a starting point, I want to share with you, or in fact remind you, the following problem that I'm sure many of you are well familiar with. And to me, that sounds like the most embarrassing algorithmic problem in the context of random graph that I can think of. We consider an Erdős-Rényi graph, G and P, on n nodes. H probability is P. It's a dense graph, so P, you think of P as 1/2. So every edge is present with probability P and absent with the probability 1 minus P. And on this graph, we consider one of the most familiar structure. We'll look at cliques, fully connected subgraphs, and we're looking at size of the largest clique. And as it is now widely known, the size of the largest clique has a logarithmic behavior on the number of nodes. And somewhat more precisely, asymptotically, it's twice logarithm with base 1/p of n. Okay, so how do we know that? We know that by standard application of the moment methods. The key thing here is that this knowledge is non-constructive, in a sense that we just know what the size of this largest object is, but we don't know necessarily how to find it in quick time. What we do know is that an algorithm, which is fairly straightforward to analyze, a greedy algorithm that just one by one picks a node, keeps neighbors of a fixed node, and discards non-neighbors, and proceeds in this greedy fashion and fairly straightforward way, is easy to analyze, but that gives you only half of the size of the largest clique. Asymptotically, it's logarithm with the same base, but only logarithm of n, as opposed to twice logarithm as n. And this was recognized already a while ago, and in 1976, Karp challenged to find a better algorithm because surely, hopefully, factor 2 appearing here can be improved. And sadly, this is still open. This is open and admittedly somewhat embarrassing because the algorithm that I just described that gives you factor 2 of optimality is extremely trivial. So one would imagine, certainly one would be able to do better with some more sophisticated algorithms, like maybe convex relaxation, maybe based on Lasserre hierarchy or whatnot. But none of this seems to work for this problem. And it's widely believed to now to be actually hard. But this is, unfortunately, we don't have a proof of that. So on the next slide, I described a fairly similar story, but in the context of sparse random graphs. So we have, we consider now a graph, a random graph on n nodes, but now every edge probability is d over n. So every edge is present with probability d over n, where d is a fixed constant. And in this context, its cliques are not terribly interesting because the cliques are going to be very small size, size 3. But independent sets are interesting. So the independent set, to remind you, is a collection of nodes that span no edges. It's the mirror opposite of the clique. And the largest independent set, while we don't know the size of it for each fixed d, and it's an ongoing effort to get tighter and tighter bounds for, say, when d is equal to 3, but asymptotically, as d goes, we know the size. Now, this asymptotics now here is a double asymptotics. First, we send n to infinity, and then we take the limit, and then we send d to infinity. And the asymptotic factor that appears in front of n is expressed here. It's roughly twice log of the degree d divided by the degree d. And somewhat remarkably, a greedy algorithm, the size of the independent set found by a greedy algorithm is half of that, just as in the case for cliques and independent sets in dense graphs, and nothing better is known. Okay. I think what's interesting about this problem is not only they are sort of interesting and cute on their own, but this has been quite sort of endemic of lots of other problems formulated in random structures. So in many other examples, many other problems exhibit this apparent gap between the optimal values that are estimable by non-constructive means methods like moment, first and second moment method on the one hand, and what we can do, the best we can do by achievable, by polynomial time algorithms. So here's the partial list of these problems. And I think that's what makes those previous two problems interesting, because they're examples of a larger phenomena that we see on and on. And examples include problems such as randomly generated constraint satisfaction problem, random k-set. In that case, one seeks to find a satisfying assignment to the random instance of the Boolean constraint satisfaction problem. Finding a maximum cut in random graphs, a proper colorings of random graphs, and so on. Another problem I listed here is something you might not be familiar, optimizing a Hamiltonian of P-spin-glass problem, but that's a problem I will introduce shortly, and it actually exhibits a very similar phenomenon. Okay, so we have this list of challenges that we would like to understand. If we repeatedly fail to find optimal solutions, probably, well, probably is that indeed these problems are hard, but we don't have a proof of some kind of an NP hardness of those problems. Maybe there's something else we can say about those problems, and understand what is the barrier, what prevents us from being successful. And a great deal of insight into that was brought by the statistical physics literature, which proposed to look at the geometry of near optimal solutions and solution space in general. Sometimes this is referred to the studying the landscape of the optimization problem. And one particular property that seems to be repeatedly coming up as the evidence of the barrier is this overlap gap property that I want to discuss in depth, and it does originate from the spin glass theory. Okay, and in this talk, what I will do is I will illustrate how this works in the context of one particular optimization problem in the context of spin glass that I will introduce. The problem will be completely self-contained, and its formulation is actually rather simple. The problem is hard to analyze, but the formulation is simple. So before that, well, judging by Jan's silence, there is no any urgent questions yet, but so I will continue. So what I want to do in the next few slides is just give a brief pictorial description of the property. It's not a formal definition. The formal definition varies somewhat from the problem to problem. And it's hard to give sort of one formal definition for all the problems, but the moral of the story is very similar. And it goes something like this. Admittedly, the problems we considered earlier were maximal clique, maximal independent set, are maximization problem. And here I'm gonna instead switch to minimization problem. So just feel free to flip a sign, otherwise it's the same story. So suppose we are solving some minimization problem. It involves some cost function L, which is, for example, minus size of the independent set, minus size of the clique, minus size of the cut, whatever is the problem you're trying to solve. Capital theta here represents the space of solutions. Over what space you're trying to optimize it. This could be a binary cube, Boolean cube. This could be a real cube. This could be Euclidean space, whatever. This is problem dependent. And what I have here as a calligraphic X indicates that the problem involves a random input. And the random input could be randomness of the graph or randomness of the matrix or whatnot. Okay, so here we have this problem, which is optimization problem with random input on random structure. So here's a somewhat formal, semi-formal definition that might be a bit hard to parse, but I will illustrate it a bit later with graphically. We will say that the overlap gap property holds if the following is true. One can find value mu, which is positive, two values nu1 and nu2 with the following property. We fixed two solutions, theta1 and theta2, which are informally mu optimal. Formally, what it means is that the value of those two solutions is not mu more than additive factor mu from the optimal value. So for example, if this was corresponding to the size of the largest independent set, then additive constant mu would be how additively away your independent set is from the largest. So it just marks some proximity to optimality. Okay, so the property holds if for every two mu optimal solutions, it is the case that there are distance between them, and often that distance has to be normalized and so on. If this distance is either belongs to this interval or belongs to the separate interval, and in other words, it's never in between nu1 and nu2. Or informally speaking, the distance between two nearly optimal solution, mu optimal solution, is either small or large. Small if it belongs to this interval, large, quote unquote, it belongs to this interval, but it doesn't fall in between. So let me show, right, so I already said that. So let me show how this could look graphically. So imagine that you plot the space of solutions, and that's a horizontal line, and space of values, that's a vertical line. Now, granted, the space of horizontal solutions is not one-dimensional. It's usually some kind of a binary cube in the context of random graphs, space of all independent sets or things like that. But let's say for the cartoon purposes, it was one-dimensional. So for each value, for each candidate solution, you have the associated value. And value could be large or small depending on what the solution is. So, okay, so we have this landscape of the solution values. The optimal value is achieved by, let's say, one solution, which is here. Now we draw a line corresponding to the height mu from optimality, and looking at all mu optimal solutions means that we're looking at below this line, effectively. So we're looking at all solutions which have value at most mu, and that cuts the space of all solutions into these regions. The first region is here, and that corresponds to values here, below mu. Second one is here, and the third one is here. Okay, so you can do that for every optimization problem, naturally. The overlap gap property says that the distances between any two solutions is either something like this, so it's small, or at least here, so it's large. So you see, if you take any two mu optimal solutions, either they have to be in the same cluster here, in that case, the distance is going to be at most here, or they have to belong to different clusters, so the distance has to be at least that much. If the width of each cluster is smaller than the distance between the clusters, then you would have the overlap gap property. So this is roughly how pictorially one can think of the overlap gap property. Okay, so we are getting into somewhat, I'm gonna pause here and let you maybe sort of dwell on that. The definition that I gave on the previous slide will recur in the context of the specific problem that I'm about to begin. So it didn't quite fully settle because maybe it's too abstract. No worries, it will recur in the context of the problem that I want to now to introduce. So a recurring theme of this line of work is that when we have the overlap gap property, and in the cases we can prove it or at least even conjecture that it holds, we can use this property as a barrier to certain classes of algorithms. And now I want to illustrate that in the context of one particular optimization problem. It's called Hamiltonian, finding a Hamiltonian of a p-spin model. So let me introduce the problem first. The problem is, it actually looks maybe somewhat ugly, but it's actually very simple to define. So here we consider a tensor, which in the case of when p is equal to 2 is just a matrix, but I have to consider the tensor for the purposes of the future discussion. So this is a tensor which has IID entries, IID Gaussian entries, mean 0. The variance depends on the size of the tensor, has to be normalized like this for somewhat obscure purposes, but it's not going to change the simplicity of the story. So here we have this tensor with IID entries. It has overall n times p entries. We're going to optimize over this tensor. So optimize how? The space of candidate solutions is just a binary cube. So every solution is just a binary vector with values -1 and 1. So B sub n is the space of all solutions. We evaluate every solution, so we pick any sigma which is a binary vector with entries -1 and 1. The evaluation of the sigma is given here. We effectively take their, well, it's a natural sort of inner product of A and the tensor power of sigma. Or put it differently, we go through all, missing upper bound here, n. We go through all the indices from 1 to n, and we multiply the corresponding entry in the tensor by the product of the entries of our candidate solution. So that's the evaluation of one particular solution, and we minimize that. And we're trying to find it as small as possible. Now, this might be straightforward, might be hard to parse. Let me just help you right away that in the special case, when p is equal to 2, this is nothing else but minimizing quadratic form. And minimizing it over, I apologize for the typo here, that should be b, and minimizing quadratic form, but only over binary vector. Okay, so this is the optimization problem. It is formulated over the random input because the entries here are random Gaussians. This raises two natural questions that we always ask. Question number one is, what's the value? And question number two, can we find it? Can we find it by polynomial time algorithms? Okay. So what I want to do next is just to share with you what we know about this problem and give you some background. As far as the first question is concerned, the question about the value, that has been resolved. The resolution was not trivial at all. It came first as in a conjectural form by a famous physicist and author of the spin glass theory development, Giorgio Parisi, back in 1979, who conjectured that the value upon right scaling, so you have to normalize the optimal value by n to get a non-trivial constant. He conjectured this value of this constant and explained what it should be. And that was formally proven by Talleyrand in 2005. This can be also found, I just noted another typo here. This is, I was referring to the book of Panchenko, not Talleyrand. So it's a first time I'm giving the slides, so lots of typos, unfortunately. I apologize for that. I'll fix that later. So there is a book of Panchenko in 2013 that describes this development. The details of this development are of no importance to us. What's important here is that if you scale the optimal solution by a factor n, there is a limit, and the limit is negative. As it turns out, when p is equal to 2, the matrix case, that limit can be computed numerically, asymptotically, it's some number, and the value of this number is again of no importance to us. Maybe just to give a little bit of intuition, let me highlight the very simple reason why this constant has to be negative. The answer is simple. A consists of mean zero Gaussians. So just by plugging an arbitrary fixed solution sigma, you get a Gaussian value itself. So it's going to be close to 0. So it's natural that by optimizing, by minimizing, you will get something even more negative. And it turns out that this is the right scaling, in which case the number is indeed negative, and it's given here. Okay, we would like to look at this problem from the algorithmic perspective. In other words, can we actually find a solution, in other words, a binary vector that evaluates to something close to this constant? And I see another typo here, it's negative here. So I'm gonna close it. I'm gonna just cover it with my mouse so that it's not confusing you. So it's the same constant that appears earlier, theta star, we just want to solve the same problem algorithmically, but maybe not literally optimally, but with some additive error epsilon. So the algorithmic goal here is given any epsilon and given tensor A as an input, find the binary vector that evaluates to theta star with the additive error at most epsilon. That's the algorithmic goal. As before, this is a problem. This is an optimization problem with random input. And okay. So what do we know about this problem? It was resolved positively, but fairly recently. Only 2 years ago, even though the problem was kind of open and sort of addressed both by physicists and mathematicians early on, it was resolved positively only recently, but only in the special case when p is equal to 2. So when p is equal to 2, just to remind you, I'm going to go in 2 slides. This is optimizing this quadratic form. So in this case, indeed, Montanari constructed an algorithm which produces a sigma such that this evaluates to near optimality. And okay, this was done using the class of algorithms called approximate message passing that I will introduce later. And that's the algorithm that we will analyze from the negative perspective in terms of hardness of the algorithm. So one caveat though, one interesting feature of the main result by Montanari is that it assumes an improved conjecture, though widely believed by physicists, that this model actually does not exhibit a form of the overlap gap property. Now, what particular form and what does it mean? I'll revisit that later in the context of our result. But basically, pictorially, it corresponds to what I've described, that when p is equal to 2, this model does not exhibit these properties of every 2 optimal solutions being too close or too far. This work was done shortly after a similar paper by Eliran Subak, who considered a somewhat related problem of optimization over the same matrices and tensors, except for the space of solutions is not binary vector, but the sphere. So the space of solutions now is continuous, but otherwise it's the same problem. He also proved it, and also proved that proved it for the cases where the overlap gap property does not hold. An interesting sort of side remark is that the conditions for the overlap gap property for the spherical models are known, and nothing needs to be conjectured. Okay. The class of algorithms as approximate message passing that I will introduce shortly came up from the following paper in the analysis as a method of analysis rather than as an attempt to solve the optimization problem. But now this is the only algorithm that we have that is capable of solving to near optimality at least some version of the spin-glass model. Okay, so I don't know if any questions popped up on the chat on the formulation of the problem so far and so on. So I assume none. So let me continue. What I want to do next is to give a general framework of the approximate message passing algorithms that have been considered not only in the context of this problem, but some other problems as well. Among others, it was used to construct a solution that solves the hidden click problem, but in the same regime that other methods also solve the hidden click problem. So it didn't break the barrier for the hidden click, but it just shows that at least it's as good as some other problems. Okay, the definition is a little bit complicated, so I'll go somewhat slow through it. So the algorithm is built on building iteratively a solution. So we start with some solution X, which is a solution to the optimization problem. So this solution X, it doesn't need to be binary. We will make it binary later on, but we start with a real valued n vector. And first we consider the following operator. We translate this vector by means of the tensor A into another vector. And it's done in a rather simple way through this expression. So each coordinate of this vector is the product of tensor A with tensored version of X, except for its power P minus 1. And the expression is here. So ith coordinate here, the I appears here as the first coordinate of A, and we build this vector. Just because this is tensors, it might be hard to parse. Let me just tell you that in the special case when P is equal to 2, then this operator is nothing else than just multiplied by the matrix. We take vector X, we multiply by matrix A, and we get another vector. So this fairly simple operator will be a building block to build an algorithm. So to build an algorithm, we need several parameters. We fix, and in some sense, the details of these parameters are not important, but the flavor is somewhat important. So I still want to go through details. We fix some truncation parameter M. We fix the horizon T. T corresponds to the number of iterations we're going to consider. And we fix some functions F, capital F and little f. These functions serve as non-linear local operators that we will use to build as solutions. All we assume about these functions that they are Lipschitz continuous. So these functions little f of t and capital F of t would look something like e to the x divided by 1 plus e to the x, something like that. It's typically, in the positive results, they're typically explicitly given non-linear but fairly tractable operators. So let me continue. So in the context when the approximate message algorithm works, so the scope of algorithms is described, as I say, by iterations. That goes something like this. We start with we fix an arbitrary vector, let's say all ones, but the details of the starting vector are typically not important. And then we iteratively build this sequence of solutions for t steps. And the way this is done is by applying this non-linearities f and little f and capital F and using the operator A in the form that is given here. Honestly, it's not terribly important to understand what's the intuition here. The intuition is somewhat important to understand the positive results. But for the negative results, it's really not super important. Basically, you can think of the approximate message passing algorithm as something like for any iteration step, you have a given candidate solution, multiply it by matrix A, and apply some local nonlinearities to it and repeat. And repeat it a certain number of times, capital T, and get some solution. For technical reasons, every solutions need to be truncated so that it always sits in a Hilbert cube minus m to m. M is just a large constant value. As a final step, because we have in the end some solutions which is fractional values, it needs to be rounded, and it's rounded in some obvious way so that the final solution is a binary cube. So this is the generic definition of the approximate message passing algorithm. It is this algorithm, so let me go a few slides back. It is this algorithm that Montanari a couple of years ago used to show that such an algorithm can be constructed. One needs to construct this little f and capital F to solve this optimization problem to near optimality. But as you anticipate, my focus here is not on the positive results, on negative results. So let me now describe that. As the first question as naturally is raised is it true that the model, to remind you, the Montanari's setup is when t is equal to 2, the matrix case, but is it true that, and he assumes no overlap gap property, is it true that the model does exhibit the overlap gap property when t is at least 4? So I will describe, as it turns out, that this is a conjecture, not the theorem. But there is evidence towards this conjecture, so I'm gonna leave it on the side. So let me first assume this conjecture is true and state the main result, specific main result that I wanted to discuss today. In a nutshell, it says that because this model is conjectured to have the overlap gap property, no approximate message passing algorithm can succeed to solve this optimization problem on random tensors that I just described. In other words, and more specifically, if mu is the parameter that comes up from the overlap gap property, then no matter how you build, how many iterations t you have, and how you build your nonlinearities f, little ft and capital Ft, and at what value you truncate your solutions, anything that is produced by this algorithm, when you evaluate it on a tensor, it will be away from the optimal value eta star by the value mu with high probability. Okay, so that's the main result. It basically says that the overlap gap property rules out, is a barrier to approximate message passing algorithms. Now, I wish is that instead of approximate message passing algorithms, I use something simpler for the demonstration purposes, but in the context of this problem, this is the class of algorithms that succeeded when p is equal to 2. So that's the kind of natural class of algorithms to try to rule out in other cases. The gradient algorithm, unfortunately, is not a competitor here, like it was in the case of independent sets. So in the remaining time, and Jan, I wanted to check how am I doing on time. Oh, you muted.
15 minutes for sure. So
okay, so I'll try to take less than that, yeah. And leave some also time for questions. So I only wish the story for the overlap gap property itself for this problem was simpler than what it is, but it is what it is. So I have to describe the way it is. So first, what is the precise version of the overlap gap property that we at least conjecture to hold for this problem of optimization of the tensors? So it goes like this. It's a slightly different version that I've described at the beginning of the talk. But this is a self-contained part of the talk. So if you haven't quite followed some of the slides that came earlier, it's totally fine. So you can still follow what I'm about to say. Let's fix two independent samples of the random tensors. So A is a Gaussian tensor and A hat is a Gaussian tensor with the same distributions. They're independent. And now let's consider an interpolation between those instances, which is built in this particular way. So tau is a parameter that goes between 0 and 1. And we sort of continuously go from A to A hat as tau varies from 0 to 1. Oops. Okay. Slide still showing fine? Okay. So why does it look like square root here and square root here? It turns out that because if you interpolate like this, then for every tau, every instance appearing here is still a Gaussian. So that's the only reason. So just by looking at the variance, turns out that this is the right way to interpolate between two Gaussian tensors so that every term in between is also a Gaussian. That's the reason for such an interpolation and nothing else. Now, the definition of the overlap gap property, it's a bit hairy, but at least it's very consistent with what I said earlier, with slight modification. We say that this entire interpolated family of tensors, continuous interpolation of family interpolating between A and A hat, satisfies the overlap gap property over the domain S sub n, and think of domain as a binary cube or a Hilbert cube, depending on what the space of solutions you look at, with parameters mu that you've seen earlier, and parameters nu1 and nu2, which are between 0 and 1. Nu1 is less than nu2, that's important. If it is the case that for any two members of this family, A1 and A2, so you fix one member of this family corresponding to some tau 1, and another member of this family corresponding to tau 2. So you fix any two such Gaussian tensors in this family. You fixed a near mu optimal solution U1 for the first one, mu optimal solution for the second one. So U1 corresponds to A1, U2 corresponds to A2. Both have to be at most mu. If every time you do that, it is the case that their inner product normalized appropriately falls into either first interval or second interval. If that's the case, then we're saying that the model exhibits the overlap gap property. This is just a formalization of the informal statement that I said earlier, that every two near optimal solutions need to be either close to each other or far. The closeness is measured by the inner product here, but it's just a proxy for the distance. The only difference here is that instead of talking about near optimal solutions for any fixed tensor, we're talking about near optimal solutions for any pairs of tensors appearing in the entire family. And that's important for the technical reasons. But otherwise, morally, it's the same definition as earlier. Okay, so the conjecture is simple to state. It states that for the Hilbert cube, when we solve to optimize the tensors of the Hilbert cube, the overlap gap property does hold when P is at least 4, and it does not hold when P is equal to 2. There is a second part of this. There is a second part of this conjecture that is purely technical. I'm going to skip it in the interest of time. And it's the first part, which is informative. Unfortunately, this is the conjecture, but the evidence towards this conjecture is that if we changed the domain from the Hilbert cube to a binary cube, then it's not a conjecture, it's a theorem. In that case, we can prove that overlap gap property holds, as was shown by myself and some co-authors recently. Now, unfortunately, for the negative result that I posted, flashed earlier, this result, because the approximate message passing algorithms evolve over the real valued vectors, then we needed a version which was also stated for the real valued space of solutions. And that's still a conjecture. The proven version of this conjecture is only for the binary cube, but that one we could not use for the negative result. I'm just gonna say one key word for the proof idea. I have more slides than that, but I'm not going to go through them in this talk, but they are on the slides and you can go over them offline if you're interested. Just a bit of a notation, sigma alg of tensor B is just the result of running the approximate message passing algorithm on the tensor B. B is a fixed tensor, so nothing is random here. The key property that allows us to prove that overlap gap property is a barrier to approximate message passing algorithm is the following kind of stability property. It informally says something very simple. It says that, okay, so we run the algorithm on instance A, and we get the result sigma. What happens if we perturb A little bit? Does it change this resulting solution drastically? And the stability property, if we have it, says that that's not the case. It's formulated here, more precise form in here. It says that if you perturb the instance over which you run this algorithm a little bit, then the answer can be quantifiably bounded. Or rather the change in the answer in the L2 norm can be quantifiably bounded in terms of the norm of the tensor itself and the difference of the two norms. The details here are not terribly important. All it says is that informally this happens. Change the instance a little bit, this resolution will change only a little bit as well. And this kind of stability is the key to the argument of the main result that I will not go through details here. The punchline of the argument says that because of this kind of stability or sort of continuity property, you can prove the result by contradiction by building a family of the instances, interpolated family instances, and interpolated family of the resulting solutions such that their overlap will fall into region where they should not fall into by the overlap gap property. So you have the proof idea combines the continuity of the space of the solutions, the stability of the solution on the one hand, and sort of lack of continuity exhibited by the overlap gap property on the other hand. This proof technique has been used repeatedly in many other cases, and what I want to just on the next penultimate slide is just to give you the list of some other problems where similar ideas have been worked out. For the first time, the idea of using the overlap gap property as a barrier to algorithm was used by Madhusudan and myself in the context of analysis of local algorithms for sparse random graphs, which was very quickly improved by Raman and Virat, who showed remarkably that in fact, local algorithms, appropriately defined as factors of IID, cannot do better than just a trivial greedy algorithm. And if you recall this factor 2 for independent sets at the beginning of my talk, this is what I'm referring to. Factors of IID, unfortunately, cannot do better than the greedy algorithm for the problem of finding a large independent set in this sparse random graphs. It was also used to show that a certain sequential version of local algorithms can't solve a version of a random k-set problem. Not all equal k-set problem. It's just a natural variant of the Boolean constraint satisfaction problem. It also was used to rule out Markov Chain Monte Carlo type algorithms, except for it's not exactly Markov Chain Monte Carlo, but something called the walk set for the same random constraint satisfaction problem, as was shown by Koja, Oglan, and co-authors. It was used also to rule out finding a large cut in a sparse random hypergraph by means of local algorithms. I missed the local algorithms here. Again, thanks. All of these results are due to the presence of the overlap gap property. That's the key technique to show these negative results. And last, let me share you with a couple of ongoing work in progress that is being written up by now. This is a work with myself and Okosh Jagannath and Alex Wine that shows, in the first piece of work, shows that the algorithms based on the so-called low degree polynomials also fail for the p-spin models, as well as the independent set models in sparse random graphs. P-spin model is the exact model that I've walked through in this talk. Independent set model is the one that I've discussed in the beginning. And likewise, something called the Langevin dynamics also fails to find near optimal solution. Langevin dynamics is in the continuous time version, continuous space version of Markov Chain Monte Carlo algorithms. So the list is growing, and it's interesting. What's missing here is some kind of a better hardness guarantee on the hardness of this problem than just ruling out classes of algorithms. Ultimately, there is a building, there's a sort of mountain of evidence that these problems are indeed hard, but we're not there yet. This is all I wanted to present today. This is the end of my talk. Thank you for your attention. And I'm gonna turn it over back to Jan.
Yeah, thank you, David. Thank you. It's thank you for the nice talk. I think actually there is a button to clap your hands. So I think participants can do that electronically, but I'm not sure. I'm sure they are doing that physically, but that can be transferred. So I think we have some time for questions. So please tell me in the chat if you want to be, So Yuval Filmus is asking, what about dimension 3, where you have you don't have this positive result and you didn't mention it among your negative results either? Oh yeah, so
I guess I didn't mention p equal to 3 is still open. I guess the only reason and the negative result would follow if the conjecture holds. It's just we don't have an evidence for the conjecture because even for the binary case we don't know if that's the case. Whereas for the binary case, we know it's the case when P is at least 4. So that's the only reason.
So you don't know where, you actually don't have a guess whether the overlap gap property should hold or not.
Yeah, we don't have a guess, and I'm not sure. Physicists might have a guess. I have to ask them, but I don't know.
So by the way, how sensitive are these results to these tensors being Gaussian?
Oh, not sensitive, but it's so good question. So it's not sensitive, but it's not clear whether the results would extend in kind of a blanket way by some kind of insensitivity results. So what it means is that most likely, let's say we replace the Gaussian tensors by the binary tensors, plus minus Bernoulli entries, it might mean that we'll have to redo all the proofs to show the same holds. There's a little doubt that they will, but it's not follows, but does not follow in some blanket way immediately. For the polynomials, though, that I mentioned earlier, so for this piece of work, it does seem to follow, if we're not mistaken, because the low degree polynomials are famously insensitive to the randomness of the inputs.
Mm-hmm. 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 By the way, is there some class or other natural combinatorial problem or optimization problems where I would tell you the gap I want to have, and you would give me such a combinatorial problem, at least conjecturally.
The gap you want to have.
So like the clique, there is this gap, say the existential versus algorithmic, there is a gap of 2.
Yeah.
So could you cook up a natural problem where there would be a gap of 7.3?
So you start with the value of the gap, and interesting. I've never thought about that, but it reminds me. I mean, these gaps, in some ways, they come up from the problems that you want to study. So one kind of, maybe for what it's worth, the connection would be with the field of approximation algorithms, where you study one problem and you see, okay, I can approximate it by factor 2, let's say in something like a vertex cover or something. I'm making it up, I'm not, let's say 0.787 for the max cut in non-random instances. So these gaps come in approximation algorithms, come from the worst case optimization problem you're trying to solve. And similarly here, the overlap gap problems come from the optimizing random instances. I never thought about doing the reverse. It's an interesting, interesting question.
Yes, I have another question. Your results rely on the existence of an overlap gap. Now, does the positive result only rely on the negation of this? So as long as you don't have an overlap gap, then yeah.
Yes, precisely. And that sort of kind of raised our suspicion that this was probably a key. So let me go to the right slide here. It's just a reference slide. Yeah, so the positive result, both this one and this one, which are for just 2 different versions of the problem, both assume that there's no overlap gap property. It's stated and it's actually assumes something slightly stronger than that, but essentially that's what it says. Slightly stronger version says that if you randomly, in some appropriate sense, if you randomly sample 2 near optimal solution, whatever this random sampling means, more precisely it means that you sample from the Gibbs measure associated with this optimization problem. If you randomly sample and look at the distribution of the overlaps, this distribution is strictly increasing, has a strictly increasing property. That means that it's, and strictly increasing property means that it doesn't have a flat part. This flat part of the distribution indicates that the support of the distribution is one continuous interval as opposed to this joint union of intervals. So that's indeed is an assumption here, which is unproven. And for this part, it's based on assumption which is proven. It's known. One can explicitly characterize the overlap gap property for the spherical p-spin models. And Eliran-Subak's result says that if you have a version of this problem which doesn't have an overlap gap property, then I can construct an algorithm.
Okay, thank you.
Sure.
Thanks a lot for the talk.
Yeah, at least one more question by you and Arlie. So Ewan, please go ahead.
Yeah, I'm just wondering, is there some other version of the overlap gap property that specifies a distribution on the gaps of near optimal solutions, or some variant like that?
That specifies the gaps of near.
So currently there's a very strict rule that says the gaps, there are no gaps of a certain size.
Yes.
Are you allowed to allow some amount of gaps of a certain size, or?
So are you asking about the positive or sort of? Okay. Let me answer this question to the way I understood it. So in the definition of the overlap gap property, let me go to the picture. Let me go to the picture here. It says that simply there is no solutions in this region. There's a version of this property which is called free energy barrier, which doesn't quite say that there is no solutions in this region. It just says that if you sample from the Gibbs distribution, then just the total number of solutions which appear in this intermediate region have exponentially smaller mass than the solutions which are either close or far. So and something let me rephrase that in the context of actually independent set problem. There's a version of this property that was shown by Koja Oghlan and Harley Eftimio. They say that every two, for almost every two independent set of larger than this size, their intersection is small or large, for almost every two, but not literally all two. But for the negative results, however, it's important that we have the strict rule of all or nothing, so to speak, because the algorithms do not have to produce a random solution. So we need to if we want to rule out the success of algorithm, we need to have this in this kind of strict form. I don't know if this answered your question or I was answering some imaginary different question.
No, that was exactly my question.
Okay, good, very good.
Thank you.
So are there any more questions? What I can do now, I can stop recording and we can move to the informal part if there will be any questions there.